Can I just buy a fourth of the cookie? What? I have to eat the whole thing? Think about it. I don't have just definite integral, just.
No, because I didn't lose the one.
Like this your. So you can see the square, but plug in a square. Hey, you're right. Oh, it's technically it's just, oh, but your expert is just.
On the board is today for this question. Let's calculate this definite integral. It's really the area below the function. Let me know if you already have the solution.
Thank you.
That's right.
16.
Let me know if they were.
You don't really put them for 30 seconds. So what did you place? I know.
Thank you. That's right. Thank you. Okay, good. Thank you. Feel free to share with your neighbor or with your calculation. Guys might be learn from each other. Good. All right. Still working on it. Illustrating my process. I will typically finish the calculating the indefinite integral and then putting the integration in it. It's kind of my usual habit. If you're able to find the antiderivative for the indefinite integral, then all you have to do is deal with numbers after the function is set. So start by integrating this function. Root of 16 minus x squared dx. Some textbook, especially physics, they treat this as formula and they have a solution for it already. But we are learning how to calculate it. We don't have any formula. Or we don't consider this as part of formula. So what we do is use what we are learning in 6.3. We're going to do a trig substitution. So x equal to, there's a 16. When we have a minus c squared, we typically do a sign substitution. But for sign substitution is 1 minus cosine squared equals sine squared. there's a 1, but here we have a 16. So we kind of have to create that 16 in our substitution. So x equal to 4 sine, x equal to 4 sine theta. Right, theta. Okay, x equal to 4 times sine theta. In this case, then the derivative dx. Try to get ready for the substitution, so we would write out everything. And then when things are calculated, we can work on. It was supposed to be theta, but cosine theta d theta. So this is the derivative of the x function multiplied by the differential. All right, once we get that, we also need to work on the substitution of 16 minus x squared. So in the root, we have 16 minus x squared. Now with our substitution, they become 16 minus x is 4 sine theta. So x squared is 16 sine squared. So we now have 16 sine squared theta. Try to write the square part. Sine squared theta. So that is the 16x squared become. And then you keep writing it, you factor out the 16. If you grab the 16, there's 16 minus 16 sine squared, so the 16 is a common factor. Take out the 16, you have 1 minus sine squared. 1 minus sine squared is cosine squared, so we actually have cosine squared. Cosine squared theta. That's what it's right. The way that it kind of looks like a theta. All right. So that's 16 cosine squared theta that was in the root. So now we're ready for the substitution. So the question, we're just working on the integration. We don't need the number yet. Inside the root, we actually have 16 cosine square theta. And then for the dx actually 4 cosine theta to theta. So it's multiplied by cosine theta d theta. So this is equal to the root cancel. The root of 16 is 4. Root of cosine square is cosine theta. And then we have 4 cosine theta. So altogether we have, this is equal to 16 integration cosine square theta to theta. I hope you know how to integrate cosine square. If not, we typically we do a power reduction formula. So this equal to 16. What is cosine square theta? Cosine square can be written as 1/2 plus 1/2 cosine 2 theta. We the double angle formula. Okay, this is a formula for the cosine square, which equal to this. So we're writing a degree 2 function into a degree 1 function because the degree 1 function can be integrated. So the integration is giving us this. So this is equal to 16 times 1/2 is 8. So it's 8 theta plus 8 sine 2 theta over 2 and then plus c. That was the answer for the indefinite integral. We also know that from the double angle formula sine 2 theta, which was what we have here, sine 2 theta equal to 2 sine theta cosine theta. So sine 2 theta over 2 would equal to this over 2. So this part essentially is equal to this. Because the 2 was canceled. So our final answer for this integration is equal to 8 times theta plus 8 sine theta cosine theta plus c. We're writing it back to the original variable. So it actually equals to the theta is this. Sine theta equal to x over 4 from that one, sine theta is x over 4. So theta is getting rid of the sine, you would use sine inverse. So theta equals sine inverse x over 4. So what happened to the a theta? A theta is 8 times sine inverse of x over 4. Right, then plus 8. And what happened to the sine? The sine theta is x over 4. So 8 times x over 4. Oh, there's cosine theta. X over 4. So here is 16 minus x squared. So the cosine theta is adjacent over hypotenuse. Cosine theta is root of 16 minus x squared over 4. So this is the entire antiderivative. Maybe not the way you think of it, but now we are finally finished integrating. So we put in integration at 0 and 4 and finish the calculation. In this calculation, the only one that actually matters is the sine inverse, because in this part, if x equal to 4, 16 minus x squared is 16 minus 16, which equals 0. The whole thing, because it's multiplication, is now equal to 0. If x equal to 0, we have x over 4, the x equal to 0, x over 4 equals 0. A times 0 also 0. So then you can see because of the 0 created by the equation limit, the only one we need to calculate is a times sine inverse. If you put in the sine inverse is odd function, because sine is an odd function, therefore odd function always has the origin. So if x equal to 0, 0 over 4 is 0. So sine inverse is 0 is 0. 0, sine inverse is 0 is 0. So the only one we have to calculate is sine inverse of 4 over 4. So this is a times sine inverse 4 over 4. That should finish the calculation. You use your calculator to calculate the sine inverse, but sine inverse of 1 actually equal to pi over 2. So the calculation is 8 times pi over 2. I hope that we are okay with the process of this. If you had the wrong answer last time, feel free to check it. About not. It's 8 times pi over 2. So the answer should be 1 pi. Okay. We can go back to the calculation. You see your name? The answer is D. It should be 4 pi. If you want to double check the calculation, I cannot guarantee if it's perfect, but this is all the steps in there. I started in the middle. The purpose is using trig substitution to calculate the antiderivative. I went through the substitution process. I tried to explain it in the detail, and then I'll go back once we find the antiderivative. I'll put it into question. So everything that was necessary is here. So that's it. Part of it that was a formula for simplification, and part of it was just getting ready for the substitution. That was also for substitution process. And then the rest of them are the actual integration. So not all of them was the integration. Some of them are writing down. Some of them were supposed to be on the scratch paper explaining the process. Any question? I hope that I did recorded your attendance for today. Do you have any homework question you want to mention? It's okay. All right. What else? Yes. Try to find the image.
Yeah.
You still don't see the paper?
No.
You lost it?
Yeah.
I see. Any other questions? Okay. Question from homework? Question from homework? Right. In that case, let's try to finish what we started. We're starting 6.6. I mentioned a little bit yesterday. Okay. 6.6, the title is called Improper Integral. What we've done so far, most of the integration that we calculate, most of the definite integral that we calculated are improper integral. By improper integral, we really are talking about definite integration. If you have the indefinite integral, we're working on the algebraic calculation to find the antiderivative. For the improper integral, we will determine the value. And any improper integral involves a little bit infinity. And that's why we're talking about value. And then with value, we're comparing. You would say some of the number are finite numbers, some of them are infinity. So we don't talk about value in the antiderivative. We talk about value with definite integrals. This is definitely related. The first example I'm trying to go through is from the textbook. We see a couple of integrations. The only thing that's different from them between them is the upper limit. You can see we can change the upper limit to higher and higher numbers, but the value didn't change very much. So it looks like the integration of the function from 0 to infinity, it could also be finite. So we have this idea that even when sometimes the integration limit are infinity, we're still able to calculate a finite area or a finite definite integral value. So it's necessary to study that kind of calculation because sometimes we do work on this kind of question. All right, this is our definition for improper integral. Our traditional definition for definite integral is for integration interval a to b. Both has to be finite. So when a is infinity or b is infinity, that's called improper integral. Another thing is in a traditional definition, the function f of x should be finite as well. If the function equal to infinity or the function went to infinity and anywhere between that interval, then the integration itself might be falling apart as well. So we want to study if that happens, when that happens will affect the value of the integral, and that's also called improper integral. Now, among the two cases, case number one, when the integration limit involves infinity, it's easy to tell because you see the infinity sign in your integration limit. You know that's going to be an improper integral. Another situation, which is the second one, is a little bit difficult to detect because let's see a very simple example. We may be doing like integration of -1 to 1 plus x. Will be like, well, that's 1 over x, right? So we might not realize that we might go like out of the absolute value of x. Let's calculate the value of 1 and -1, subtract them, and that will be wrong because the function 1 over x, when x equal to 0, 1 over x is undefined, and 0 is one of the number between -1 and 1. So our x value is from -1 to 1. So 0 is right in the middle of -1 to 1. At 0, the function is undefined or equal to infinity. So we have that problem. This is the improper integral. And sometimes people forget that or not noticing it. The second type of improper integral, even I make mistakes because I have a habit of looking at integration. I have antiderivative. Let me do the calculation. And we often make mistakes because you do that. You may accidentally think the answer of the integration is 0, but it's not. It's actually undefined integral. Right, so we do have to pay attention to that, but luckily we don't deal with that a lot. Just this section. All right, let's talk about how to handle the infinity. All right, in calculus, a way to handle infinity. All right, to begin with, the notion of infinity is artificially defined. When you see the number lines from -infinity to +infinity, we're actually saying that as human, we're not capable of drawing infinity, but we are capable to understand the notion that this side goes on for on and on. This side of the number line goes on. We're just saying that the number can be large with no definite ending of it. So the concept of having an infinity on your number line is artificial. but it has its purpose. A lot of time, because we don't have a definite upper limit. You can see the upper limit is 1,000, just like this example. Or you can see the upper limit is 1,000, 10,000, or 100,000, but you cannot explain the idea that, in fact, 0 to infinity, integration of 1 over 1 plus x squared dx is roughly 1.57, that idea. So having an infinity there just indicating whatever large number you put there, you always end up having something at that value. So using infinity as notation, it kind of combine a lot of different scenarios and give you a freedom of expressing that idea. So anyway, what do we do? The infinity is the limit idea, and therefore, whenever you have infinity, we understand that we handle it with limit notion. So here is how we gonna calculate, and or how do we determine the limit? The improper integral can be calculated, or improper integral equal to a finite number or infinite number. We gave some terminology to it. So if we want to calculate a integration of f of x from a to infinity, what we're gonna do, we find a way to calculate the limit from a to finite number b, right? We calculate that. Once we have a formula for the calculation, we then let b go to infinity, and then this limit would be the integration value of a to infinity of function f of x. So if we are capable of calculating the integration on a finite interval, and then we can calculate the integration on an infinite interval just by letting one of the integration limit go to infinity. We find something like a function of the upper limit. All right, another situation is, what if the lower limit of your integration is infinity? Again, we treat it the same way. You calculate, you use a finite number as your lower limit and find out a formula for that definite integral. And then you will make a go to infinity. If this limit exists, and then this integration is finite, then you have an improper integral that converge. Right, the last situation is, what if the upper limit and the lower limit both equal to infinity, negative infinity to positive infinity? So how do we do? We kind of have to separate them into two, just pick any number between negative infinity, positive infinity, possibly 0. So integration on a big interval can equal to integration on a smaller interval added together. So the integration from negative infinity to positive infinity can equal to integration from negative infinity to 0, and then plus integration from 0 to infinity. We can separate them into two integration and treat it the same way as 1 and 2. So that's how we do it. You can integrate from number to number c. And the lower limit goes to negative infinity. Plus this time you go from c to b, and b goes to positive infinity. So summation of these two will give you the total integration value. So this is how we're gonna handle this kind of integration. And we then have this idea of converge or diverge. These are two of the terminology we mentioned in calculus 1. That is, when you have limit, and we see this limit or this function converge. When the limit value equal to infinity, or when the limit value does not exist, we see it diverge. So since we are using limit to study improper integral, whenever the integration has a limit, when this integration value has a limit, at the infinity, we say the integration, the improper integral converge. If the limit does not exist, then we say diverge. So basically, the improper integral, if it equal to a finite number, then it converge. If the improper integral does not equal to a finite number, or it doesn't exist, then we say diverge. Any questions? So it follow the same reasoning, same matching of the terminology with calculus 1 about the limit notion. Let's look at some calculation example. All of those are just talk about terminology and definition, Now we're gonna look at how do we calculate when we are facing individual question. Here we have 4 questions. We're gonna try to look at them one by one. Start with the first question. Let's integrate 1 over x squared on the interval 1 to infinity. Here, let's look at the first one. So what do we do? Instead of calculating integration from 1 to infinity, we calculate 1 to a being a number that we don't know. Because what's the infinity? Infinity is arbitrarily large number in a sense. So number 1, if you make it a finite number, can you calculate it? Once you have a number, let's make that number go to infinity. Let's separate the process of calculation. You do integration first, and you do that limit next. So on the board, I have the integration question. If you're integrating 1 over x squared, what is 1 over x squared? Is x to the -2 power. Same as the denominator, -2. So power is -2 using the power rule. -2 plus 1 is -1. So x to the negative power over -1, which equals negative x to the negative power. -1 power is 1 over x. So -1 over x. That's integrated. Any question? The process of time, it can be reversed. You will try to grab 1 over x and find the derivative of it. According to the quotient rule, of course, you will denominator square, you should follow the quotient derivative. So anyway, once we find the nth derivative, we're going to put in the integration limit. They were a and 1. If x equal to a is -1 over a. If x equal to 1 is -1 over 1. So we minus -1, so plus 1. So about the integration process, any question? So now we're going to look at the limit calculation. If you want to calculate the integration from 1 to infinity of the same function, compare these two calculations. Since we already have the answer on the interval of interval 1 to a, all we have to do is make a go to infinity. So this integration equal to a go to infinity of -1 over a plus 1. If a go to infinity means this fraction, the denominator goes to infinity. The limit of 1 over infinity or 1 over a arbitrarily large number, that's limit equal to 0. So this is basically 0 plus 1. 0 plus 1 equal to 1. Any question about the process? Okay, when you have like a 1 divided by another number, this number goes to infinity. Think about 1 over 10,000, 1 over 100,000, 1 over 1,000,000. You see the number getting smaller and smaller. That's why we see this limit is 0. I hope that kind of makes sense about the limit calculation. And so now we have this first answer. Integration of 1 over x squared on the interval 1 to infinity, the answer is 1. So that converge because it equal to a finite number. And moving on, I'm going to try to pair these two together because these two are very similar. One is integration of 1 over x squared. This is the integration of 1 over x, but the answer is totally different. This is another function on the same interval 1 to infinity. We're integrating 1 over x. To handle it step by step, we're going to first put an integration limit that was finite. So you integrate 1 to b, number b is a finite number. So the answer for 1 over x is different because 1 over x power is -1. Whenever the power is -1, we cannot apply power rule because you have to go power plus 1. -1 plus 1 is 0. We don't want to deal with the denominator. So we have to figure out the nth derivative. For 1 over x, nth derivative is natural log of x. So now we're putting integration limit. So it's natural log of b minus natural log of 1. ln1 equals 0. That's just ln b. Any question about the integration formula? So we had a little variable in the answer, but we specifically follow the integration formula that we learned before. Now it's a limiting process. Okay, moving on, we want to calculate the limit of the integration 1 over x on the interval. That means once you have the answer for the finite interval integration, you're making the number b go to infinity. So that's pretty much like calculating logarithm of infinity. The answer is equal to infinity. like ln of 1,000, ln of 10,000, ln of 1,000 of 1,000. You see the number getting bigger and bigger. The limit process when b go to infinity is b getting larger and larger and larger. What happened to the ln of b? You can see the ln b is getting larger and larger when the b gets larger and larger. So that's why we see the limit equal to infinity. Any questions? Now, when the integration equal to infinity, it means this integration, this improper integral diverge. So we don't have a finite value for it. Okay, so it actually have a geometric meaning for when we have this calculation. We can actually graph this function. And what we did was on the interval 1 to infinity, we don't have to graph the whole function. Y equal to 1 over x squared. It looks like this, but we're not graphing the whole function. Or we're only graphing it from 1 to infinity. 1 to infinity, I guess we have the boundary. So this is what happened. Right, according to what we calculated, the integration from 1 to infinity equal to 1 means that the area that's below the red curve, you see that's 1, okay, and that's a little bit less. So you can, if you take the 2 to 3, that part to fill out that part, I mean that was 1, like square 1, right? Area equal to 1. This is actually smaller, and this going that it means that everything that you see below the red curve, try to fill the rest of them to get a perfect square. You have to fill all of them there. The whole area below the red curve is 1. That's our calculation, right? Our calculation is point 1. Now let's look at the second example. We got 1 over x. But of course, the graph looks like this. So we only calculated for x bigger than 1. Okay, so that's what we have. So our calculation is showing area below this curve, you see, is slightly higher than the 1 over x squared. But how high, you have to kind of see what's going on to the rest. Like everywhere it goes, it's slightly higher to infinity. Of course, we keep going. But according to our calculation here, it's infinity. So it turns out the subtle change that degree 2 changed that degree 1. The total area below the curve of 1 over x is actually infinity. I mean, it's infinite long strip of area. This one is 1, meaning that majority is in this first square. All the other ones are small enough that you can fit into a little square. Any question? So you can see the power in the denominator really make a big difference. Let's move on to other examples. Let's see how we calculate this one. We're calculating integration of negative infinity to 0 of e to the x. And we're doing the same thing. Number 1, we will switch out the infinity for a number. So we're integrating a to 0 e to the x. Now, e to the x is not too hard to integrate because the antiderivative is itself. E to the x, differentiate or integrate it, it's the same thing. So we have to calculate a definite integral. The integration limit is 0 to a, so e to 0 minus e to the a. While your calculator, or you maybe you already know, e to 0 equal to 1. That's 1 minus e to the a. Now let's look at what happened to the limit. And 1 minus e to the a. Now, if we want to calculate the integration of e to the x on the interval to 0, we have to make a go to negative infinity. All right, so limit of 1 doesn't matter what a1 is not being affected by a, it's still 1, and the negative still negative. So limit of e to the a when a go to negative infinity, what will happen? The answer is 0. So how do we know that? It's like you're calculating e to the negative infinity. Somehow I write it that way, so it's easier to tell what we're doing exactly. So what would be the negative? Negative is division. So e to the negative infinity is really 1 over e to the infinity, or the actual calculation is 1 over e to what is super large number. See, all you have to do is put 10. Okay, you can use your calculator. 1 over e to the 10, really large, the denominator is really large, so the whole thing is really small. So that's roughly 0. I mean, this we're supposed to e to the infinity, right? E to a really large number. You can go 1 over e to 100. Your calculator is gonna tell you that's 0. It is small. So I'm trying to use my own way to explain that limit of e to the a when a go to infinity is 0. Are we okay? And so then the answer is 1. So under the curve e to the x, the area between negative infinity and 0 is roughly equal to 1. That's the third example. The fourth example, we're integrating 1 over 1 plus x squared on the negative infinity to infinity, which will be the whole number line above the whole number line, the whole x-axis. What would the area below the curve 1 over 1 plus x squared? So how do we do it? Number one, let's try to look at what does it mean. I graph the curve of 1 over x squared. Cannot really graph infinity to negative infinity to infinity. So you can see majority is in the middle when x value is really small, really big, it gets really small. So we want to find out this area, whether it's finite or infinity. That's really the purpose of the calculation. All right, so first thing we want to do, we're probably going to break down at 0. So we're going to calculate what is it, this integration from negative infinity to 0 and from 0 to infinity. Why do we do this? Because we're doing a limit calculation. You can only handle one side at a time or one limit at a time. So we separate them into 2 calculations and do it one by one. Let's see the first one in this integration of this function from negative infinity to 0. And again, we switch on the lower limit for a number a. So integrate from a to 0, 1 over x squared. The antiderivative of 1 over x squared is tangent inverse. Tangent inverse calculate from 0, a to 0. So we have tangent 0. Tangent inverse 0 minus tangent inverse a. Tangent inverse 0 actually equals 0. So it's 0 minus tangent inverse of negative infinity, and that gives us negative pi over 2, which gives us a positive 2 in question. So how do we know the tangent inverse negative infinity equal to negative pi over 2? We can do this. We can do tangent inverse, all your calculator. Do tangent inverse of 10,000. You can see it's roughly 1.57 or something pi over 2. I mean, that's a numerical way to look at it. Another way would be looking at the graph of tangent inverse of x. The whole function goes negative pi over 2, slowly growing, and almost level down at positive pi over 2. So tangent inverse is positive pi over 2 when x goes to positive infinity, negative pi over 2 when x goes to negative. Any question? It's a similar process for the other side. You can integrate this part. If you integrate a function from 0 to infinity, you first will integrate it from 0 to b, and I'll give you tangent inverse b minus tangent inverse 0. And then again, tangent inverse 0 equal to 0, so tangent inverse b, when b go to infinity, is pi over 2. So both of these two have, this is pi over 2, that is pi over 2. So the total integration is pi over 2 plus pi over 2, which equals pi. So the final answer for the combined calculations will be pi. Isolate our main result. This is the all the calculation for the fourth example. Improper integral that involve in infinity interval have the integration interval. Case number 1. Any questions? If there's no question, let's look at another example. Okay, so this example, when you first look at it, it's not much different from what we already have. The only problem would be the function is not very easy to integrate. But we kind of know how to integrate it from the integration by parts. So what we're gonna do is looking at how do we integrate it. So I see if I cannot integrate the antiderivative, if I cannot find the antiderivative, I won't be able to do it. Even the integration is fine. Even the interval is fine. So just look at the antiderivative of the function. I'm using the integration by parts. So LIATE. L is logarithm. I is inverse trig. T is A is algebra. T is trigonometry. E is exponential. Anyway, this is a logarithm. The logarithm can only, it should be your u. LIATE is the choice of your u. So if you have logarithm, you would use the logarithm equal to u. If you equal the natural log, so u equal 1 over x dx, and then everything else is your dv. dv is 1 over x squared dx, therefore v is negative 1 over x. That's the antiderivative of x to the negative 2 power. You can integrate this with power rule. This is derivative, that's the antiderivative. Remember the integration by part of the function is differentiated with differentiated natural log. Part of the function is integrated, we're integrating 1 over x squared. All right, with that, we start building this. This middle part is really assisting us for identifying the proper integration or reduce the level of difficulty of the integration. According to this original question, by our identification, the integration of UV equal to integration of UV minus integration of VU. So this is the UV, U times V, okay, minus integration of the VU, these two combined, 1 over x squared. Okay, and then 1 over x squared, if you integrate it, is negative 1 over x. We have it. That's our antiderivative. And then if you want to integrate this function, now that we already have the antiderivative, the calculation will follow through. Any questions so far about the integration process? So this allows us to know the formula for the calculation. Now since we already have all that, that means if you are integrating this function, not from 1 to infinity, from 1 to b, we're integrating 1 to b, so 1 to b, how do we calculate it? We already know the antiderivative. All we have to do is add on the integration limit. So if the integration limit is 1 to b, we're going to calculate the antiderivative value at b and also at 1. So if we write it out, it will look like this. How to do it step by step. So we plug in b, it's negative natural log of b over b minus 1 over b. The upper limit, lower limit is when x equal to 1. Natural log of 1 equal to 0, which is negative 0 over 1 minus 1 over 1. That's minus 1. Okay, and then notice that natural log of 1 equal to 0, so that's 0. Negative plus 1. So now we have negative natural log of b over b minus b over 1 over b plus 1. So this is illustrating the integration of the function from 1 to b. B is a number. So what do we do next? Yes, so we'll work on the infinity. So next, since we're integrating from 1 to infinity, after we find the limit of a finite interval, we are now calculating the actual question. Right, so we're calculating some other question because we want to lower the difficulty. If we want to calculate the integration of the function from 1 to infinity, we'll have to make the b go to infinity. And we have a formula of the integration already. All we have to do is make b go to infinity. to b approach infinity. Now here we have three term, the limit of 1 still equal to 1, limit of 1 over b if b go to infinity and 1 over infinity. 1 over a really large number. That was 0. 1 over b is equal to 0. Now this one, we didn't do it because we want to look at the detail. The calculation of that is a little bit, little bit time, less time or more explanation. Because if b go to infinity, the denominator is b. The denominator go to infinity. Numerator is natural log of b. If b go to infinity, natural log of b also go to infinity. So this is infinity over infinity case. According to calculus 1, when you have 0 divided by 0, or we have infinity divided by infinity, you could apply L'Hopital. So we can calculate limit of L and B over B using L'Hopital's rule. So here we are. According to L'Hopital, we will find the derivative of the numerator and denominator separately. Derivative of L and B is 1 over B. Derivative of B by itself is 1. So L'Hopital have two derivative calculation, one in the numerator, one in the denominator. So we're not doing quotient rule. We're doing two separate calculations of quotient because they're comparable. When the original function are going to the same direction, the derivative of the direction. So we're turning a limit calculation that was originally hard to do to a limit calculation that's slightly easier to do. So the purpose of L'Hopital is not calculating the limit, is making the limit easier to calculate. So this new limit calculation is now calculating limit of 1 over b, or limit of 1 over b. When b go to infinity, limit of 1 over b equals 0. So find the answer 0 plus 1. We have this whole integration also equal to 1. Any question? All right, what do you want to, if you want to compare this, because we already have a calculation, like integration of 1 to infinity of 1 over x squared, it was equal to 1. And now this one also equal to 1. So it turns out, even though they have different function, they have the same integration value, improper integral have the same. So it's kind of interesting to say, sometimes when things are different, they cause drastic, like when things are slightly different, they cause drastic difference. And sometimes when things are really, really different, but they actually equal for some reason. It's kind of interesting. I think we calculated that one, right? The example number 1 is integration. It's integration 0 to infinity, 1 to infinity, 1 over x squared dx equal to 1. Now we have this example. Final answer is also equal to 1. Let's work on the second type of improper integral, and this is the one that I consider slightly harder than the one that has infinity. I mean, to me, I'm not afraid of difficult question as long as I know which part is difficult, which part is easier. The scary part is that they're coming at you without you noticing it. So it's more scary when you think the question was really easy, but it turns out really hard. And this is the kind of question. So we will have to identify the discontinuity of the function. And we don't, well, I don't always pay attention to the function if it's always continuous or not. When the function is end up being undefined, we also have to pay attention to it. So how do we handle the function that has the infinite range, or when the function value itself becomes infinity? Often when the function value itself become infinity is because like 1 divided by 0. And that causes the function to be undefined, but it causes the limit of the function to go to infinity, right? So having any undefined point or having any asymptote, virtual asymptote is one of the main concerns. This kind of question is when you have a finite interval of the function, but the interval is finite, but the function f of x itself went to infinity. So it's not a horizontal infinity, it is a vertical infinity area that we can calculate. Right? How do we handle this kind of question? The same thing. You want to add one more breaking point on the interval calculation. So for example, integration of a to b, if you have a discontinuity at c, so c is a point that function have a problem, so you will calculate integrate from a to c, and then plus integration from C to B. At the point C, you're gonna look at a limit and calculate them one by one. So that's just breaking down. If the discontinuity is on the edge, then you don't have to break them into two. But if it's not on the edge, you have to take the edge and separate your interval into two intervals. See, how do we calculate? That was just conceptual, like really abstract notation for how do we handle this kind of thing. Let's look at actual questions. Right? These two are not the same. The one on the left, if you know what's the problem, our interval is 0 to 1, which was finite. But then 1 over root of x, 1 x equals 0, we have a problem because 1 over the 0 is undefined. So this function, the discontinuity occur at the boundary. So what do? You don't touch the 0 at the beginning. You let the number go to 0 in the end. That's how we handle it. So this one, you don't have to break down to calculation of integration. Now, the one on the number 2, where is the discontinuity? It's still at 0, right? If x 1 over 0 squared, which will be undefined. So 0 is right in the middle of -1 and 1. So what do? We write this one into 2 integration. So you integrate -1 to 0 of the function plus integrate 0 to 1 of the function. And you calculate those two by itself and then add it together. So the treatment of these two are different because the discontinuity occur at different location. One on the edge, one in the middle of the interval. In question. Let's look at the calculation. All right, so we look at what happened to the first one. That was this being presented in the textbook. If we graph 1 over root of x on the interval 0 to 1. So here is x equal to 0, and the right boundary is at x equal to 1. X is between 0 and 1. Y is 1 over root of x. Way over here, it goes up. All right, because as 0 is undefined, so the function is going closer, never touch the vertical line. So you won't be able to arrive at any point. It will keep going and until infinity. Right, so that's what happens with function graph. So we notice something that the function is finite at 1 or anywhere below 1 until we have this issue at 0. So 0 is what we call the vertical asymptote because at 0, the function is forever getting closer and closer to the vertical axis, but never touch it. We keep going, we never arrive on the y-axis. And that's why this thing goes on and on and on. The height of the curve is going to be, okay, that's going to be a problem. So how do we do it? We still going to do the same thing. We don't calculate 0 to 1 because we know 0 is a problem. So we calculate a to 1, and we're going to find a formula for this. And then all we have to do, if you've got a formula for this calculation, you make a go to 0, and then we'll find the final answer to the integration. So now, how do we integrate this? This is x to the -1 power. So we can actually use our power rule for the integration. If you're integrating x to the negative, it's in the denominator, so it's -1/2 because it's a root. Root is 1/2 power and then dx. So in order to integrate this one with power rule, we got x to the -1/2 plus 1 over -1/2 plus 1. That's the antiderivative. So what's -1/2 plus 1? It's positive 1/2. So this is actually x to the 1/2 power over 1/2. And that's 2 times x to the 1/2 power. And that's 2 times root of x. So the antiderivative of the function is 2 times root of x. So it's really short on the screen. I'm trying to explain it how we apply power multiplication. Any question? All right, so you know how to calculate it. We're going to plug in the 1 to the antiderivative and also plug in a. So lower than it is a. So we end up having this 2 times the 1 minus the a. That's our antiderivative. That's final answer for the definite integral. And now what we have to do is make a go to 0. So if we're calculating 0 to 1 of the function, we have to make a go to 0 from the right side because we don't allow A go to -0. These are intervals 0 to 1. How do you get closer to 0? You go to any positive number and you get closer. So 0 to 1 are usually kind of approach 1 or approach 0 only from the right side. So x is the positive 0, just to see. We have positive 0 there. If this is a negative number, we have a problem, right? The root of negative number is undefined. So anyway, when a approaching 0, root of 0. So this is our answer. The final answer is 2. So this integration actually converge because we have a limit that equals 2. Any questions so far? So this is how we handle the first example because the discontinuity of the function occur at the boundary of the integration interval. All right, let's get the second question. How do we do it? And I write my wrong answer because I made this kind of mistake before myself because sometimes I didn't pay attention. It's just outright follow the power rule. Integrate 1 to -1. -2 was the final answer, which is incorrect. So what do we do? Notice what happened, the graph of 1 over x squared. It will have a like infinity at x equal to 0. So when x equal to 0 function, as x get closer and closer, like this is a trend. You have to keep going. There's like forever getting closer and closer to the y-axis. You can see the area in the middle. So I have a feeling this kind of be infinity because you see a large area there. So how do we calculate it? Anyway, this is similar to how do we treat a lot of integration questions. You see a problem in the interval in the domain of your function, you identify that problem point, you make it visible, right? So if you look at the original integration, the 0 is hidden there. And this is when you don't deal with 0 at all. I mean, that's going to cause a problem in the final answer. You have to make 0 something that you have to handle. So integration of the function from -1 to 1 actually equal to the summation of 2 intervals. Here you break down the interval into 2 parts. -1 to 0, then 1, then 0 to 1. So -1 to 0 and 0 to was supposed to be a 1, 0 to 1 of the function. So you have these 2 integrations and we're going to calculate them one by one. So first we're going to handle this first one. The calculation of it will be you make the upper limit not 0. You can't calculate 0, 0 is out the time. So then calculate t. So you integrate -1 to t, 1 over x squared. The antiderivative is -x over 1. And you're going to plug in t, plug in -1. So it's -1 over t minus 1. And then when t goes to 0, this is undefined. So we can see that the infinity on the left is the interval value on the left is infinity. Integration value on the left is infinity. Let's see, first half, we end up having an integration value that equals infinity. The other half, all right, if you integrate from 0 to 1, I mean, again, 1 is no issue. 1 over 1 is fine, but 1 over 0 is undefined. We don't make the limit, the integration limit equal 0. We make it t to 1. Then again, we already have the antiderivative, -1 over x. And we're calculating it at 1, calculating at t. Again, we're supposed to make t approaching 0. This time is from the positive side. It was -0, that was positive 0. But either way, and that's going to make that one equal to infinity. So this, again, has a limit that equals infinity. So the integral is infinity. So it's infinity, and both area on the left and right equal to infinity. I kind of agree with the picture that we see. Either side of the 1 over x squared, it goes up, and you have a big area that we calculate. The area in that picture is actually infinity. Area below the curve is infinity. Any question? This kind of confirms some more things. So that basically saying even if we integrate 1/x² from 0 to 1, still missing the one, copy and pasting, and still equal to infinity. Right? Remember, if we're integrating 1 to infinity of the 1/x², it was actually 1, but then integrate from 0 to 1, it actually equal to infinity. So we can see the behavior of 1/x². It looks different on either side of the drive. You draw y to 1/x², it looks like this and this, because it's symmetric, right? X being positive, negative, the same, right? And then you find this number 1. Right? The total area from 1 to infinity is what we calculated before. It was 1. This area equal to 1. The total area from this part, it was actually infinity according to our calculation. Other than that, this is -1. This is also infinity, and this is also. So you have some better understanding about the area below the 1/x² curve. Okay, so then since it's equal to infinity, so it doesn't equal to a finite number, therefore the integration, the improper integral diverges. Have that conclusion. Instead of saying this equal to infinity, that does not exist, or this equal, we will just simply just say it's diverge. As long as you don't have a finite number for the answer, we say diverge. Any question? So now we're gonna try to understand a little bit better. That is maybe for all those integration from 1 to infinity, 1/x to the p being 1, 2, 3, 4, 5, any power at all, maybe 1/2. We want to find out what's causing it to converge, and what kind of p will make sure it diverges. So we're really trying to determine if there's any patterns like we can observe in how the power in the denominator affected the divergence of the entire integral. We're hoping to find some patterns and things or some rules that governs the value. And you can do that by a lot of graphing, or you can do that by a lot of examples. We already have 2 examples. Number 1 is have integration 1 to infinity 1/x² is equal to 1. Let's try the same thing over there. Number 2, we already have the example that if you're integrating 1 to infinity 1/x is equal to 1, that equal to infinity. So basically say if p equal to 1, the integral diverge. If p equal to 2, the integral converge. So we kind of have the idea. Maybe bigger number will cause us to decrease faster, so converge. So the area of the low part will be finite. So maybe for smaller power, like p equal to 1, maybe p 0.5 to go to the lower side of the p value, they'll diverge. And then how do we understand it a little bit better? We certainly have to do some calculation. So what do? We essentially wish to calculate this, right? Those are just special cases on the left, and we're trying to put a general idea on calculation. You may have some like the individual example that kind of give you some hints, but we still have to theoretically study it. Again, when we try to look at improper integral, we always kind of have to understand the infinity. We switch out the infinity to something less large. We put on the finite number b, and then make b equal to infinity once we have the formula. So if that was b, right? So this is a 1/, so it's negative power x to the negative p power, according to the power rule, x to the power plus 1 over power plus 1 power rule. And we make x equal to b and x equal to 1. If x equal to b, then b to the 1 minus p minus 1 to the 1 minus p. And notice 1 to the 1 minus p equal to 1. Then this one is okay, and then when we figure out if there's limit. So next thing is we're gonna make b equal to infinity and see what happens. Now, to calculate this integration, we have to make b equal to infinity because the upper limit is not a b, it's infinity. So if b equal to infinity, what happens? We need to know 1 to the 1 minus p power. That's just 1, but b to the 1 minus p power, we have to study it. It affects it will be affected by the 1 minus p. The main question we have to ask is whether 1 minus p is positive. To see it clearly, if the power is positive, the function is going to be increasing. So b to the 1 minus p power, if 1 minus p is positive, which means 1 minus 1 is bigger than p, or p is less than 1, or if that's the case, we get a positive power, this function goes up. So therefore, if b go to infinity, the whole thing also go to infinity. That's divergence. So if b is less than 1, we can see it's going to diverge. But if 1 minus p is negative, if 1 minus p is negative, 1 minus p negative means 1 less than p bigger than 1. So if p bigger than 1, then 1 minus p is negative, and that means this function is 1 over b to a positive power. So then if it's negative means division, that means b, the power function of b is in the denominator. In that case, if b is in the denominator, b go to infinity, of course, the whole thing will have a limit that equal to 0, right? Because the denominator goes to infinity, right? We want to see if b is in the numerator or in the denominator. That will be affected by the power. If the power is negative, be in the denominator. If the power is positive, be in the numerator. And that's why we have to tweak that. Any question? Are we okay? Hopefully it's not too confusing. We already have a conclusion that p equal to 1, it would diverge. So the middle one, we already have that answer. The first one and the last one are by looking at this formula. So we end up knowing that for smaller power, it will diverge. And as long as it's bigger than p, so if the power is slightly higher than 1, it will converge. For example, integration of 1 to infinity 1 over x to the power 1.1, really small power, small but bigger than 1, of course. The whole thing actually converge. But the converge value, this calculation is 1 over 1 minus p. So the bigger p will cause the whole thing to have a smaller area. This it was 1 over p minus 1. So when the denominator is bigger, when the p is bigger, it converge, but it converges to a smaller. Makes sense? Exact calculation already giving us -1 over 1 minus p. That's your integration value. Because we're expecting this b when b go to infinity, this one b to the 1 minus p go to 0. That one goes away. Are we okay? This discussion not only tells when it's converged, when it diverged, it also tells us the actual value of the improper integral. It's right there, the improper integral. If it converge, that's when p is bigger than 1. Therefore, b to the 1 minus p power will have the limit of 0. So it's 1 over 1 minus p, 0 minus 1. So it's 1 over p minus 1. That's the integration value. The negative cancel. Any question? So we have that rule that allows us to identify the convergence diverse behavior of a 1 over power function on the larger limit. This is our summary. And how do we calculate area below a negative power function? Negative power being the power function in the function, 1 over a power function. What we were talking about was over here. If you have a really smaller p is less or equal to 1, then the integration diverge. If the power is high, right? 1 over, when the power is higher than 1 over a big power, remember what happened to the power? What happened to the x? X goes to infinity. So 1 over the infinity, 1 over a really large number will be a really small number. So the whole integration actually to converge, right? For smaller p, if the denominator is smaller, and what happened to the infinity? If this power is smaller, I guess we have 1 over a smaller power. infinity. So it's not small enough that will actually cause the integration to be larger than necessary. Any question? So this is the upper half, and then lower half is the other one. What if we have a smaller integral? What if we integrate from 0 to a finite number of 1 over x of p? You see, if it's a power function in the denominator, when x goes to 0, it will have a discontinuity. So this is a two type of discontinuity. This one has infinity integration limit. This one does not have infinity, but it has discontinuity at 0. So this one we have to study using the second type of improper integral. So the second case, the lower one, is the one we didn't talk about. So we can still go through the process. It's integration from 0 to 1. So 0 is a problem. So what do? We're gonna calculate integration from b to 1 instead of 0 to 1. But then again, the antiderivative is similar. It's like 1 over 1 minus p x to the negative p plus 1. Same thing, power rule. And our integration limit is b and 1. We're gonna find the value at 1, the value at b, it will look like this. And now we have to make b equal to 0 to see what happened. Now we need to know what happened when b equal to 0. Now, if b equal to 0, you need to answer this true question. Is the power positive or negative? 1 minus p is the power. If it's positive, that means b is less than 1. So b is less than 1, then the power is positive, and b approaches 0. 0 to a positive power is 0. So that's when it converge. On the other case, if the 1 minus b is negative, so if the power is negative, then the b is actually in the denominator. So you go 1 over b, denominator of b goes to 0. Now 1 over 0, if the denominator equals 0, it's undefined or infinity. So that's when they diverge. So you can see the power b to the 1 minus p power the power really affected the power of the limit equal to what value the limit equal to, or diverge, converge. That's why we separate them into two cases, p bigger than 1, then 1 minus p being negative, and not the b is in the denominator, b equals to 0 will cause infinity. That's why it's diverge. If p is less than 1, that means 1 and p is a smaller number, 1 minus a number smaller than 1, which means 1 minus p is positive, then b is a number that has positive power. When b approaches 0, there's just a 0 to a positive power, which equals 0. That means it's finite, that means it's converged. I hope I made it clear. Are we okay? Well, so kind of flip it, right? When you integrate from a positive number to infinity, functions, you expect the p to be larger or to be converged. But now we are integrating from 0 to 1 or 0 to any positive number. 0 is a problem. So what happens to 0? What do you expect to the power? It would certainly want the power to be smaller. Yes, they do. Yes, they make calculators. That's what the whole thing. Any question? All right, so hopefully this is summarized. This calculator will help us to try.
Little knows where it is.
I guess this is
That's kind of crazy. Activists.
They could make like pipeline, like technology, calculators. Pipeline that may be ridiculous.
Well, So here we'll call one over x squared. When x is one over yes. For example, it's different questions. So for example, maybe we have a summation of one over x minus one. Let's say we're integrating from one to then there was one would be a problem in this case, right? Let's say we're integrating. Okay, in this case, for the function one over x minus one squared. X total, it will become one over one minus one squared, which will make it undefined, so it's not equal, right? So the one would be followed. This calculation, you have to calculate what happened at one, so go 0 to 1 of same thing. And then plus 1 to 3. 1 over yes. So the same integration you have to run it twice. Because one is
He doesn't.
one minus 1 0. So one is causing that one. That's why we have one.
Information.
Doesn't think if you attend online, you I don't know.
So they're, but they're, the exams are. Yeah, exactly.
I will post them online.
Did you have any? What? Did you have any? Yes.
It will be the same.
Dr. Adam, for.
You watching the videos?
So good about.
You can always do that. So even if you attended in class, you can still watch the recording later. Okay. If you are in class, it's easier to add